Hi everybody, welcome to another episode of the tinyML Talks. On behalf of tinyML Foundation, I'm going to chair this session. My name is Danilo Pau, ST Microelectronics. Today I have the privilege to introduce you Philippe Leong, Chief Technology Officer, CruxML Pty Limited. He is Professor of Computer Systems, School of Electrical and Information Engineering, University of Sydney. The title of this talk is Low Precision Inference and Training for Deep Neural Networks. I think this is going to be a great talk. But before to leave the floor to Professor Leong, let me remind you the list of the tinyML strategic partners. They are a lot, and thanks to them, these and other events are possible. So let me remind you who they are. AI Zip, Analog Device, Arduino, ARM, Compass, Edge Impulse, Green Waves, Groverty, IBM, ImageBot, Innatera, Microsoft, Nota AI, NXP, OctoML, Pauline Technology, Pixel, Qualcomm, Renesas, Schneider Electric, Sensimi, Sony, Silicon Labs, ST Microelectronics, Synaptics, Cynthian, TDK, Inference. So between the many resources, the tinyML community offers different formats for you to enjoy and to acquire information. One is the meetup. The community is growing. We have currently 14K members in less than 50 groups in close to 40 countries. And there is a vibrant community also live in LinkedIn. These are the links. Please refer to them in order to get more and more information. Information that are also available through YouTube with 9K subscriber, lots of few hundreds of video with a awesome number of views. So if you want to get advantage of all the content that tinyML Foundation share to the YouTube channel, please do so. And you can really get up to date on tinyML from different angles and different perspectives. Important to remember, EMEA 2023 is going to happen June 26, 28 in Amsterdam. More sponsorship are available. If you are interested, please write to sponsorships at tinyml.org. Short bio to introduce Professor Leong. He received BSc, BE, and PhD degrees from University of Sydney. In 1993, he was a consultant to ST Microelectronics in Milan, Italy, working on advanced flash memory-based integrated circuit design. From 1997 to 2009, he was with the Chinese University of Hong Kong. He is currently professor of computer systems in the School of Electrical and Information Engineering at the University of Sydney, visiting professor at Imperial College, and Chief Technology Officer at CruxML Pty Limited. So for me, it is a privilege to leave the floor to Philippe Leong. Thanks so much, Philippe, for your availability and to find time to present your latest research interest and results to the tinyML community. And I leave the floor. Thank you.
Yes, thank you very much, Danilo. I'll just begin by describing our laboratory, which is called the Computer Engineering Laboratory. We focus on how to use parallelism to solve demanding problems, and we strive to develop novel architectures, applications, and design techniques, mainly using FPGAs. And our research is in reconfigurable computing, which is the application of FPGAs to computing problems, and trying to use machine learning to solve radio frequency problems. I'll begin with some motivation about this work, and we can usually trade off performance and precision. GPUs and CPUs are designed to support data types of fixed word lengths. So they're efficient for operating on doubles, floats, longs, shorts, and chars. And as we go from these wider word lengths, say from 32 bits down to 1 bit, we can use the same area to improve the number of operations per second that we can do. So, you know, if we were to fill a chip with 32-bit operations, we could perhaps do about 0.3 tera operations per second. But if we can take that down to 8 bits, that would be 4 TOPS. And if we could go all the way down to 1 bit, which we can for inference in machine learning, we can get up to 66 TOPS. And also our ability to store weights on chip goes from 2 million weights for 32-bit all the way up to 70 million weights for 1-bit systems. So these are 200 times potential improvement in compute and 30 times improvement in weight storage that we could potentially utilize. Now, FPGAs and ASICs allow us to develop computing machines with custom data paths of arbitrary word length. And so the main thing that I will talk about today is how we could utilize low precision for inference and training. This talk is in 3 parts. First, I'll talk about our work on a type of arithmetic that we call Block Minifloat. And then I'll talk about the application of Block Minifloat to time series prediction, and finally on transfer learning. So this Block Minifloat work was done by Sean Fox when he was a student at the University of Sydney. And as we've mentioned, training, well, sorry, we haven't mentioned this, but training has a greater efficiency problem than inference, in that for training of neural networks, we require about 3 times more multiply accumulate operations, and it has much higher memory requirements. And prior to our work, a number of specialized number representations have been proposed, which are alternatives to 32-bit and 16-bit floating point systems. And the range that we're interested in are using 4 to 6 bits for the weights, activations, and gradients. And as we know, the training of neural networks are computationally expensive, particularly for the large language models, which are really expensive in terms of compute and also memory intensive. And so we believe that there's some opportunity to reduce the precision that is used for training. And, you know, this can lead to cheaper and faster training systems. We are focusing on the edge. We're not sure whether these lower precision formats, which of course don't converge quite as well as the higher precision counterparts, you know, whether they will be useful in the data center. I'll begin by describing mini floats. Now, a normal floating point number has 3 fields: the sign bit, an exponent field, and a mantissa bit. And, you know, in binary 32 and other IEEE 754 formats, these are of a certain number of bits. The range that we're interested in is 4 to 8 bits. And what we call a mini float is just the same as an IEEE 754 type, except with smaller exponent and mantissa fields. We have chosen in our mini float system to not support not a number and infinity. Now, the advantages of mini float are that we use fewer bits so that we can save memory. And this also leads to smaller hardware for their implementation. The disadvantage, of course, is mainly in dynamic range. If we have a small number of exponent bits, we can't span a wide dynamic range. And of course, we lose in precision when we reduce the number of bits. So that's a mini float. A block mini float, in an analogous way to block floating point, is we take a mini float tensor and we share an exponent bias across blocks of n by n mini float numbers. So if this tensor is in some format, we're dealing with 2D tensors. So we always, if it's a high dimensional tensor, we break it into a 2D one, and we make it n by n floating point numbers, and then we have one shared exponent bias amongst them. So it's an additional bias. And that's what we call a block mini float tensor. The shared bias gives us wider dynamic range, and we can operate on these mini floats, and we can produce denser dot products in hardware than a data type with wider word length. When we operate on our block mini floats, we basically have to think about the way we align them. If the yellow part of this top figure on the right here is the range that we can represent, we may have to represent tensors with a value distribution. This is a log scale on the x-axis here. We may have to represent numbers with a value distribution that's bigger than what we can represent in mini floats. And so either we have to drop some bits in the low part or the high part. What we have chosen to do is that we will align our mini float system through this shared exponent with the maximum exponent values. So what we do is that the mini floats can represent this range in yellow. With the shared exponent, we'll shift that down so that it's aligned with the maximum exponent. And then the part on the left, we will allow underflow. And so we will lose some precision in the low bits of our arithmetic. Block Minifloat is actually a generalization of the number systems that we typically use in for low precision machine learning. So if we think about arrays or tensors of fixed point numbers, they just have the mantissa field, except usually in 2's complement format. With an array of mini floats, we have the sign, the mantissa, and the exponent bits. Block floating point uses shared exponents and fixed point numbers. And for block mini float, we have shared exponents and mini floats. Another crucial part of the block Minifloat is that we use a fuse, multiply, and add with Coolidge accumulation. So in a Coolidge accumulator, we apply a fixed point accumulator, which is wide enough to compute the error-free sum of the floating point products. So in this figure, we have A and B that are in Minifloat format. We do the multiplication, and we have to do a shift, and we change it into a fixed point format. And we have this large accumulator in fixed point, in which we can represent the whole range of the Minifloat number. So actually, block Minifloats with exponents up to 4 bits yield this maximum number of bits of the mantissa product to be about the same size as a 32-bit integer arithmetic unit. We use 3 techniques to reduce the data loss of our low precision arithmetic. We support gradual underflow. We arrange it in blocks, as I've discussed at length. And we support hybrid formats. And I'll talk a bit about each of those, particularly on the next slide. In this work, this first part of the talk, I'll talk about our the accuracy results that I'll report, our block Minifloat hardware, which is simulated on GPUs using 32-bit floating point arithmetic. The way that it's organized, we apply block Minifloat to all of the weights, activations, and gradients. And because we're using this Coolidge accumulator, we get the same results for in block Minifloat as we would with 32-bit floating point. After we've quantized the inputs to 32 bits, then because we compute the exact multiply accumulate values, then we will we get the same result as 32-bit floating point. We have defined a number of block Minifloat formats. So for our 8-bit format, we use 1 signed bit, 2 exponent bits, and 5 mantissa bits for the feed forward path. And for the back propagation paths, we use 4 exponent bits and 3 mantissa bits. So it turns out that if we do it this way, we get the best results. We have other formats. So for example, our 6-bit format has 2, 3 for the feed forward and 3, 2 for the back prop. Usually we desire more range for the back propagation parts. And then in fact, if we go to 4 bits and if we select 0 mantissa bits, then this is actually a logarithmic number system. And so we have actually done experiments with 2130 and also 3030, which is entirely logarithmic number system. We did a number of experiments which are detailed in the paper that I'll have a link to at the end of the talk. These plots show epochs on the x-axis and the value of the loss function on the y-axis. And the green trace shows the result for 32-bit floating point. And if you use 6-bit block Minifloat, but with no denormalized numbers, then you actually get the red trace here. It doesn't converge at all. But when you add denormalized support, then you can see that the 6-bit training gets the same result as the 32-bit training. So denormalized numbers are crucial. Support for denorms are crucial for this, this arithmetic system. This figure in the middle shows the trade-off between area and range. So of course, as we change the block size, if we go to smaller and smaller blocks, then the area cost increases. And that's shown here in red. And then it starts to flatten out. And we want to be operating where the area is low. So we want to be operating where this red trace is flat. Also, the range that we can support reduces as we increase the block size. So we strive to be in this flat, in this region in here. And so we're operating somewhere block sizes between 2 to the 5 and 2 to the 6. As we change the exponent base, we can see this plot on the right shows the exponent base versus the root mean squared error of the numbers that we compute. We compute this one with a set of dynamic experiments. And so the red trace shows underflow, the occurrence of underflow. So we want to be in the flat region where underflow doesn't occur too much. But we also want to minimize the root mean squared error. You can see that between 1.5 and about 2.5, there's a flat area where the root mean squared error is at a minimum. And we found that our strategy of scaling the block so that it aligns with the maximum exponent puts us in this flat region here. And so we normally operate here with a base of about 2. The way we tested training with block Minifloats is that we began with the GPU, and end-to-end GPU training, what we do is that we take our initial input and our weights, and these are quantized to block Minifloat. Because of the way that our computations are structured, we can use the CUDA gem library, the CUDA library on the GPU to do all our operations in 32-bit floating point, and the result is actually the same as the block Minifloat value. When we do the backward activation gradient, we do the same thing, and then the weight upgrade, the weight gradient and update, we use a similar technique. Now, the weight activation and gradient tensors, when we quantize them to block Minifloat, we use stochastic rounding, and the Coolidge accumulator ensures that our dot products are exact, which is why we can use the 32-bit floating point CUDA library directly. And we use 32-bit floating point for Coolidge to floating point conversion, for block Minifloat alignments, quantizations, etc. Doing it this way, we have approximately one floating point operation every n multiply accumulates, and simulating this block Minifloat arithmetic on a GPU, we incur a 5 times slowdown, which is much lower than other types of low precision formats for training. We ran a number of training experiments. This one is ResNet 18 on ImageNet, and the x-axis are the epochs, and the y-axis is the validation accuracy. Floating point is in red, so that's this lowest line. But you can see that when we do 8-bit block Minifloat and 7-bit block Minifloat, and all the way down to 6-bit block Minifloat, we get essentially the same validation error. This purple line is 5-bit block Minifloat, and as you can see, it still converges. It's just that because of the quantization, we're not able to achieve as low a validation error. Surprisingly, it works all the way down to 4-bit block Minifloat values. And if we look at the final result with the difference in the validation error, we actually get, about 0.6 to 2% better results for block Minifloat than floating point. This is just due to the stochastic nature of training, but it's very similar in terms of validation error. We also tried this on a small transformer model. So the blue score is on the y-axis here, which is the figure of merit, and the epochs are on the x-axis. And it's slightly worse than, higher is better. It's slightly worse than 32-bit floating point, but you can see we achieve a very similar result for this transformer. We ran a number of training experiments, including AlexNet, EfficientNet, and LSTM and SSD Lite. And in each case, we achieved very similar training accuracy to 32-bit floating point. As you can see, 56 versus 56.2 for AlexNet and ImageNet, 62.6 for floating point, and 61.8 for block Minifloat 8 for EfficientNet. And for LSTM, 84.7 versus 87.33. We basically can conclude that the training accuracy for these networks with block Minifloat were very close to 32-bit floating point. We took we made a design of a fuse multiply and add unit, as well as a 4x4 systolic matrix multiplier, and synthesized it at 750 megahertz target frequency with the Cadence RTL compiler using a 28 nanometer cell library. If we compare the area and the power of different number formats, FP32, so binary 32 format, takes about 5,000 square microns, and the power is about 10,000 microwatts. And when we go down to a 8-bit block Minifloat format, it's about 10 times smaller in terms of area and 10 times smaller in terms of power. It's actually comparable to an int8 data type with a 32-bit accumulator. And if you look at our Block Minifloat 8 compared to int8 for the systolic matrix multiplier, again, the area is similar to int8 and the power is similar to int8. And this is at a bit better than half the area and half the power. So as a general rule of thumb, the 8-bit block Minifloat area and power are comparable to int8. We also compared our 8-bit block Minifloat with some other number systems that have been proposed. And here, this is computational density. So this is sort of computation per area, and top one accuracy is on the y-axis here, and 32-bit floating point is here on the left. It has excellent accuracy, but its computational density is not so good. So shifted and squeezed FP8 is the S2 FP8 here from Stanford and Intel, and it requires 2 more bits than our work for that's this one here. It requires 2 more bits than our work for similar accuracy. And also they use a high precision master copy of their weights. For the hybrid 8-bit floating point format, HFP8 here from IBM TJ Watson, they require different formats for forward and backward passes like us. And our system has better computational density. So as we reduce the number of bits, of course, our computational density improves. However, this is the cost of top one accuracy. And this is for ResNet 18 on ImageNet. So I've talked about the 8-bit block Minifloat format. Now I'll talk about our work in implementing this using FPGAs. And our first application is in time series prediction. And these are initial results. And Wenjie Zhao is actually working on this at the moment. So just to recap, the work that I just presented used GPU implementation, and we also had a 28 nanometer ASIC study. Here we explore the FPGA implementation of N beats, and we look at both inference and also training. And we study the implementation of a block Minifloat gem array, so matrix multiplier array, and a accelerator architecture. NBeats is a time series prediction model, and it's from a paper called Neural Basis Expansion Analysis for Interpretable Time Series Forecasting, which was presented at ICLR 2019, and it's a paper from Benjo's group. It achieves state-of-the-art time series prediction results, and the neural network comprises mainly of fully connected layers with shortcut connections. So it uses blocks, which are a stack of fully connected layer and ReLU nonlinearity. There are 4 of these layers, and then there's actually these are used to compute a backcast and a forecast. These blocks are then arranged in a ResNet-like organization where there are these pass-through connections which are summed with the output of these NBeats blocks. So the forecast is the sum of these n beats blocks. That's the prediction output. And the backcast comes down here and uses the residual connections. We developed Inference accelerator architecture. The main blocks are a Block Minifloat matrix multiply here with a Coolidge to Block Minifloat converter and a vector adder here on the left-hand side. And we also have a unit which does exponent alignment and ReLU, and 3 buffers to hold the intermediate results of our calculation. We used systolic linear systolic architecture for our gem, and each processing element performs multiplication and accumulation. The intermediate results are stored in this purple Coolidge buffer, and the result transformed to a Block Minifloat format. In terms of accuracy, we use SMAPE as the metric, which is the y-axis here. And the orange results on the left for yearly, quarterly, monthly, and daily predictions are in orange. And you can see that our 8-bit Block Minifloat in yellow achieves very similar accuracy to the 32-bit floating point and better than the 8-bit integer in green. So for this example and with this accelerator, we again conclude that the accuracy of our 8-bit Block Minifloat is similar to 32 bits. Here is the resource utilization of an FPGA implementation. This is just inference for the moment, and the gray shows the number of DSPs. These are block RAMs, registers, and lookup tables for 16-bit floating point. The orange one is 8-bit integer, and the blue one on the bottom shows that we use fewer DSPs than even 8-bit int. We use little bit more in terms of ultra RAMs. In terms of block RAM, we use very similar to int 8 with 32-bit accumulators and few more registers and lookup tables. We again conclude that the area of Block Minifloat 8 is similar to int 8 and smaller than FP16. In terms of inference performance, the power of all the 3 implementations measured on the FPGA board itself is that they're all about the same. In terms of peak performance, we can fit more we can fit a larger matrix multiplier on the FPGA, and so for int 8 and Block Minifloat, we can get a higher peak performance of about 200, close to 300 GOPS. And in terms of latency, we can reduce that from 354 to about 230. And the frequency, we can achieve 300 megahertz with Block Minifloat and int 8, and about 200 megahertz for FP16. Now, I describe a different accelerator, and this is for training. And basically, it's similar in that we have a matrix multiplier unit, and we have a vector add unit, but we also have another unit that does stochastic gradient descent. And we have a slightly different arrangement here. We use a 2D systolic array in this case, and we have the Block Minifloat MAC unit is the processing element, and we have an array of these, and we take inputs into the rows and columns for the matrix multiplication, and we create a 2D gem array. These are preliminary results for NBEAT's accuracy for training. In terms of the loss for FP32, we get 12.92 as the smallest loss value, and it's 12.93 for 8-bit Block Minifloat. And actually, in fairness, sorry, this is Block Minifloat 8-bit with 2.5 for the weight activation, and the error and gradients are 0.7. If we change this format to a block floating point format, we actually get slightly better results, and we can use a 0.7 format, so 0 exponent bits and 7 mantissa bits here. And even if we go down to 4-bit Block Minifloat, we still get a reasonable loss of 14.46 using a 2.1 format for the weights, 0.4 format for the activations, and the activations we make unsigned values, and it's 14.47 if we use 2.1, 0.4, 0.3, and 0.3 for this configuration here. The final part of this talk, I'll talk about our work in transfer learning, which is being done by Leong. And we believe transfer learning is a good application for edge devices. We can keep the data private and secure because we don't have to upload any personal information to the cloud. We can adapt to changing conditions so that we can deal with non-stationary data. And we can, by using things like Block Minifloat, we can reduce size, weight, and power, and we can converge to a good solution faster by doing pre-training before we, so pre-training offline before we apply the application at the edge. This is a convolutional neural network training workflow, and what we do is that, as I've mentioned before, training of both NBEATs and convolutional neural networks has 3 times the workload of inference. So in the forward part, if we're implementing a convolutional layer, then we want to do convolutions. And in this accelerator I'm going to describe, we do this with arbitrary stride. So not only do we support stride 1 convolutions, we support 2 and 3. For the backward propagation, we apply what's called a transpose convolution for the backward part with respect to the activations. And for generating the gradients with respect to the weights, we apply a dilated convolution. And so we actually have these parts here. We apply the forward pass with this first convolution. The backward part is a transpose convolution, and then the gradient generation we use to compute the delta W's, which we then update the weights with. We've developed a ResNet 20 and VGG-like accelerator, and we have layer-wise convolutional neural network blocks. Unlike the work that I described earlier, we decided to use a unified Block Minifloat representation. So rather than have different representations for the forward and backward passes, we only use 2 exponent bits and 5 mantissa bits for this work. That means that we can have a single matrix multiplier, and that improves our utilization. We have a simplified multiply accumulate unit and a fused batch norm and ReLU unit. The main blocks are the unified convolution, which we use to do the convolution and the transpose convolution, and a dilated convolution block, which is separate. So this is the unified convolution block here. And then we have this separate transpose convolution block. So these are the 2 main blocks in our design. We actually took the ResNet 20 and we made one small change to it, in that ResNet 20 looks like this. And the batch norm and the ReLU are either side of this this residual adder here. And because we wanted to fuse batch norm and ReLU, what we did is we put them together here. We moved the ReLU before this add, and we actually verified for VGG-like network and ResNet 20 that our modifications for Block Minifloat actually achieve very similar results to 32-bit floating point. So this is for Cipher 10. And for ResNet 20, Cipher 10, it's 90.27 versus 89.87. And for the SVHN benchmark, similarly, we get results very close to 32-bit floating point. Here is a slide about our transfer learning application. What we did is that we pre-trained the model using Cipher 100, and then we took these model parameters and we froze the initial layers, and then we fine-tuned some of the final layers using stochastic gradient descent. And this was for a Cipher 10 target data set. So if we do training from scratch, then the iterations versus the loss graph shows this. We get these. This red one is the software implementation. And if we use transfer learning, then we get this purple training curve, because we've pre-trained the weights and it converges faster. So when we do transfer learning, we get faster convergence. And because we're only fine-tuning some of the layers in our network, we have reduced block RAM for activations in the backwards parts. In terms of resource and power, we compared 3 different implementations. One is a full update where we update everything. And then in a second one, we only update 6 convolutional layers and the fully connected layer, and then 2 convolutional layers in the fully connected layer. So for full updates, we use more block RAMs, about double the number of block RAMs, but all the other resources are about the same. This is for the ResNet 20 accelerator. I won't talk about the results for the VGG-like accelerator, but they're actually similar. And in terms of power consumption, all three are about the same. And here is a breakdown of latency. So for ResNet 20, with the full update, the total takes about 3 milliseconds to do. And if we run ResNet 20 on the SVHN with 6 convolutional and fully connected update, this is reduced to about 2.2 milliseconds. And then this final one with ResNet 20 on Cipher 10, we can with only 2 convolutional layers and the fully connected layer updated, the latency is reduced to about 1.6. So in conclusion, we believe that low precision formats have wide applicability for inference and training in edge applications. And using these low precision formats doesn't necessitate a reduction in accuracy. We believe that it's possible using block Minifloats to achieve faster training than the current practice. And that's because we use fewer bits to store the numbers, and that's important for memory-bound problems. And we use narrow exponents, which allows us to achieve denser multiply accumulate structures in hardware for compute-bound problems. And we're currently thinking about what are the good applications for this type of technology. The main reference for this work is this first paper, ICLR 2021, a block Minifloat representation for training deep neural networks. And the NBEAT's inference work was published in the proceedings of the Asia Pacific Conference on Circuits and Systems. By the way, in this paper, the Block Minifloat paper, we have a link to a GitHub repository which contains all the source code to reproduce the results in the first part of this talk. And all of our Block Minifloat code is open source. So I can be contacted at philip.leong@sydney.edu.au. And I thank you very much for listening to this talk. And if you're down in Sydney, we'd love to have visitors, and we would very much like to discuss tinyML with you. Thank you very much.
Thanks a lot, Philippe, for your great talk. Been very appreciated. We are close to 1 hour at the end of our 1 hour slot. There is space for very few questions. Edward Jones asked, have you compared the Block Minifloat formats to Unum POSIT formats?
No, we haven't. I have been asked this by others, and it's something which is of interest, but it's work that we haven't done.
Okay. A general question from my side is how the community can take benefit from the Block Minifloats you just described in various scenarios. If they tomorrow would like to start to use it, then how are you going to enable in their framework that?
Mm-hmm. That's a good question. So we have put all of our work on GitHub and made it open source, so that should facilitate companies to start. We would encourage them to take our code and try it out and see whether it produces the results that they want. And we're working on our hardware implementations, which we intend to later also make open source. And we're also happy to work with companies that are interested in this and work with them.
Let me see if there are other questions. No. You know that I'm quite involved in tinyML with on-device learning working group. In your opinion, what are the greatest advantages that Block Minifloat can bring in future hardware accelerators to supporting on-device learning?
Well, I think that in all of the cases that we've tried, and need to point out that the kind of largest networks that we've tried are these small transformer and ImageNet with ResNet like networks. We've put this Block Minifloat 8-bit in, and it's worked very well from the start without having any parameters to tune and without any difficulty. So probably, Block Minifloat might not be the final solution, but we believe with, we've shown the feasibility of training with 8-bit types, and it's quite robust in that if you do training with other types of number systems, there are parameters that need to be tuned, and it doesn't always work. So we're hoping with more research, we can decide on an 8-bit format which can support training. And of course, as we know, if we can go to a smaller format, we can improve performance. So hopefully this will, not necessarily 8-bit Block Minifloat, but some 8-bit format will be supported by the major vendors moving forward, and there'll be improved networks network topologies to exploit 8-bit hardware.
Thanks so much, Philippe. I would love to continue to discuss with you on this topic. However, we are reaching the limit of our time slot. So let me also express once again gratitude for your time and your availability to attend and to speak about your latest developments on Block Minifloat with very interesting aspects that you shared with us today. Thanks so much. Your time has been really appreciated and your dedication of today. So as you certainly understood, these and other episodes of the tinyML talks are possible thanks to the support of our strategic partners, which helps these initiatives and many others. So we and I express gratitude also for the support of today they provided. Let's list our executive strategic partners, which are Edge Impulse, Qualcomm, Sentient, and the Platinum strategic partners that are Renesas, Aetrios, the Golden strategic partners, which are Analog Device, Arduino, ARM, Innatera, Microsoft, SensiML, ST Microelectronics, Synaptics, and all the silver strategic partners, AIZIP, Compass, Greenwave, Gravity, IBM, Imaging Mob, Not AI, NXP, OctoML, Olin Technology, Pixel, Schneider Electric, Silicon Labs, PDK. Remember that tinyML is a registered trademark of tinyML Foundation. Thanks again also to tinyML Foundation to make it happen. Without its tireless work, this would not be possible. So thanks a lot, Olga, especially for your dedication. Evgeny, Ira, thanks a lot for making it happen and to help the community to stay up to date with all the information that also Philip shared today. So we are, I would like to remember that the video and the presentation will be available in the tinyML YouTube channel and the forum respectively very soon, tomorrow or close to. Thanks a lot again, Philippe. Really has been a pleasure to share the session you attended and in which you presented this interesting information. I think, and I hope the community enjoyed and will enjoy it also later watching the records. And let's stay in touch. Thank you so much.